The first time I saw the number, I thought it was a typo. 10 to the power of 120. Written out, that is, a 1 followed by 120 zeros. Not a measurement error, not an approximation gone wrong. This number appears in serious physics reviews published in peer-reviewed journals describing what might be the largest discrepancy between theory and observation in the history of science. The discrepancy concerns empty space. Specifically, how much energy empty space should contain, according to quantum field theory, versus how much energy it actually appears to contain according to observations of the expanding universe. Quantum theory predicts that empty space should be extraordinarily heavy, dense with energy beyond comprehension. Observations of the cosmos indicate that empty space contains almost nothing, a whisper of energy so faint that a cubic meter of vacuum holds less energy than it would take to lift a single gram by 50 nanometers. The mismatch between these two numbers is not 10%, not a factor of 2, not even a factor of 1,000,000. The mismatch is approximately 10 to the 120th power. That is, a 1 followed by 120 zeros. This is the vacuum catastrophe, and it represents one of the deepest unsolved problems in fundamental physics. It suggests that something is profoundly wrong with how we combine quantum mechanics and gravity, or that some unknown mechanism cancels almost all the vacuum energy with a precision that borders on the absurd. By the end of this video, you will understand what vacuum energy is, how physicists calculated that enormous theoretical prediction, why observations demand a value 120 orders of magnitude smaller, and what this mismatch tells us about the limits of our current understanding. If you find value in explorations like this, in understanding why physicists consider empty space one of the strangest things in the universe, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. Let me start with what physicists mean by vacuum energy, because the concept is stranger than it sounds. In classical physics, empty space is genuinely empty. Remove all the matter, all the radiation, all the fields, and you have nothing. A perfect vacuum contains zero energy, zero activity, zero anything. Quantum mechanics change this completely. In quantum systems, the lowest energy state, what physicists call the ground state, is generally not zero. Even at absolute zero temperature, when a system has the least energy it can possibly have, there remains a residual energy that cannot be removed. This is called zero-point energy. The simplest example is a quantum harmonic oscillator, a mathematical model that describes many physical systems from vibrating atoms to electromagnetic field modes. In classical physics, you can bring such an oscillator to complete rest, removing all its energy. In quantum mechanics, you cannot. The Heisenberg uncertainty principle forbids it. The oscillator retains a minimum energy even in its ground state. Quantum field theory extends this idea to fields that fill all of space. The electromagnetic field, for instance, is not just a way of describing light and electric forces. It is a quantum object that exists everywhere, even in regions where no photons are present. In its ground state, the electromagnetic field still has energy, the zero-point energy of all its modes. The vacuum of quantum field theory is not empty. It is the ground state of all quantum fields, a state with specific properties, specific energy, specific fluctuations. These vacuum fluctuations are not merely theoretical abstractions. They have measurable consequences. This brings us to a question that seems simple but leads to deep confusion. How much energy does the vacuum contain? In most of quantum field theory, this question does not matter much. The absolute value of energy can be shifted by adding a constant, and since only energy differences are usually observable, you can set the vacuum energy to zero by convention and proceed without difficulty. Gravity changes everything. Let me go deeper into what quantum field theory actually says about empty space, because the details matter. In quantum mechanics, particles are described by wave functions that encode probabilities. Where is the electron? You cannot say exactly. You can only give the probability of finding it in various locations. Quantum field theory goes further. Instead of particles being fundamental, fields are fundamental. The electron is not a tiny ball moving through space. It is an excitation of the electron field, a quantum of the field's energy in a particular configuration. Every type of particle corresponds to a field. There is an electron field, a quark field for each type of quark, a photon field for electromagnetic radiation, and so on. These fields exist everywhere, filling all of space. So, particles are what you get when you excite these fields. The vacuum, in quantum field theory, is the state where all fields are in their lowest energy configuration. No particles exist because no fields are excited. Yet, this state is not empty in the classical sense. Each field mode, each possible oscillation pattern of the field, has zero-point energy. This is not optional. It follows from the Heisenberg uncertainty principle. You cannot pin down both the position and momentum of a quantum system simultaneously. For fields, this means you cannot have a mode with exactly zero energy and exactly zero rate of change at the same time. The zero-point energy of each mode is half the photon energy that would correspond to that mode. For a mode with frequency f, the zero-point energy is half times Planck's constant times f. Summing over all modes gives the total vacuum energy. The sum includes modes at all frequencies, from very low to very high. At high frequencies, there are many modes packed into each frequency range, so the contributions pile up. Without a cutoff, the sum diverges. Infinite energy. This is one of the infinities that renormalization handles. In non-gravitational physics, you can absorb the infinity into redefinitions of physical parameters and proceed. The absolute value of vacuum energy does not affect particle physics calculations. In gravity, you cannot absorb it so easily. In general relativity, Einstein's theory of gravity, energy is not just something that affects motion. Energy curves space-time. All energy gravitates, regardless of its source, regardless of whether it comes from matter, radiation, or the vacuum itself. This means the absolute value of vacuum energy matters in gravity. You cannot simply redefine it away. If the vacuum has a non-zero energy density, That energy curves space-time and affects the expansion of the universe. Einstein himself introduced this possibility in 1917, just 2 years after completing general relativity. He added a term to his equations called the cosmological constant, usually written with the Greek letter lambda. This term represents a constant energy density throughout all of space, a property of empty space itself. Einstein originally introduced the cosmological constant to create a static universe, one that neither expanded nor contracted. When observations in the 1920s showed that the universe was actually expanding, he reportedly considered the cosmological constant his greatest blunder and abandoned it. For decades afterward, most physicists assumed the cosmological constant was exactly zero. Empty space had no energy. The universe expanded because of the momentum from the Big Bang, slowing down over time as gravity pulled matter together. Everything changed in 1998. Two independent teams of astronomers studying distant Type 1a supernovae as cosmic distance markers discovered something unexpected. The expansion of the universe was not slowing down, it was speeding up. Something was pushing the universe apart, counteracting gravity's tendency to pull matter together. The simplest explanation was the cosmological constant, Einstein's abandoned term. A small but non-zero energy density of empty space, acting as a kind of anti-gravity, could explain the accelerating expansion. Observations since then have confirmed and refined this picture. The cosmological constant, or something that behaves very much like it, appears to be real. Empty space has energy. The question is, how much? Let me give you the observed value, because understanding just how small it is makes the problem vivid. The best measurements come from the Planck satellite, which mapped the cosmic microwave background radiation with unprecedented precision. Combined with observations of how galaxies cluster and how the universe expands, these measurements pin down the energy density of empty space. The observed vacuum energy density is approximately 5.89 times 10 to the negative 27 kilograms per cubic meter. In imperial units, that is about 3.68 times 10 to the negative 28 pounds per cubic foot. These numbers are almost impossibly small. Let me put them in perspective. The vacuum energy density corresponds to about 3.5 proton masses per cubic meter. A proton is the nucleus of a hydrogen atom, weighing about 1.67 times 10 to the negative 27 kilograms. Take a cubic meter of space, remove everything from it, and the vacuum itself contributes the equivalent mass of roughly 3.5 hydrogen atoms. Another way to feel this number, the energy in a cubic meter of vacuum is approximately 5.29 times 10 to the negative 10 joules. That is the amount of energy it would take to lift a 1-gram object by about 50 nanometers. A nanometer is a billionth of a meter, the scale of individual molecules. Lifting a paperclip by the width of a DNA helix requires more energy than a cubic meter of empty space contains. By any human standard, this is effectively nothing. The energy density of vacuum is so small that you would never notice it, never measure it with ordinary instruments, never detect its presence in any everyday situation. Yet, This tiny energy density dominates the universe. Here is why that matters. Energy density describes how much energy exists in a given volume. Space is vast. Integrate that minuscule density over the volume of the observable universe, and you get an enormous total. Roughly 68.5% of the total energy content of the universe comes from this vacuum energy, which cosmologists call dark energy. Dark energy is not matter. It is not radiation. It is the energy of empty space itself, and it drives the accelerating expansion that astronomers discovered in 1998. Now let me explain the theoretical prediction, and this is where the catastrophe appears. Quantum field theory tells us that the vacuum is the ground state of all quantum fields. Each field has modes, oscillation patterns at different wavelengths and frequencies. Each mode contributes some zero-point energy to the total. To calculate the vacuum energy, you sum up the zero-point energies of all field modes. The problem is that this sum includes modes at all wavelengths, down to arbitrarily short distances. In practice, physicists introduce a cutoff, a shortest wavelength or highest energy beyond which the calculation stops. This is not cheating. It reflects the fact that we do not know what physics looks like at extremely short distances. Our theories are incomplete, and the cutoff acknowledges that incompleteness. The natural cutoff comes from quantum gravity. At the Planck scale, roughly 1.616 times 10 to the negative 35 meters, quantum effects and gravitational effects become equally important. Below this scale, we expect that space-time itself behaves differently, and our current theories break down. Physicists calculate the vacuum energy using the Planck scale as a cutoff. The result is staggering. The Planck density, a natural density scale built from fundamental constants, is approximately 5.15 times 10 to the 96 kilograms per cubic meter. The corresponding energy density is about 4.63 times 10 to the 113 joules per cubic meter. Compare this to the observed vacuum energy density of 5.29 times 10 to the negative 10 joules per cubic meter. The ratio is approximately 8.8 times 10 to the 122. This is why the mismatch is commonly described as 10 to the 120th power. The exact number depends on conventions, on which cutoff you use, on how you define the comparison. Different choices give slightly different exponents. What does not change is the fundamental problem. The theoretical prediction is incomprehensibly larger than the observed value. Pause for a moment and try to absorb what that number means. Let me explain the Planck scale more carefully, because it plays a central role in the vacuum catastrophe. The Planck scale is constructed from three fundamental constants: the speed of light, Planck's constant, quantum mechanics, and Newton's gravitational constant from gravity. Combining these constants in particular ways gives units of length, time, and mass that are natural for physics involving both quantum mechanics and gravity. The Planck length is approximately 1.616 times 10 to the negative 35 meters. To appreciate how small this is, Consider that a proton has a diameter of roughly 10 to the negative 15 meters. The Planck length is 20 orders of magnitude smaller than a proton. If you scaled a proton up to the size of the observable universe, the Planck length would scale up to roughly the size of a proton. The Planck time is the time it takes light to travel one Planck length, approximately 5.39 times 10 to the negative 44 seconds. This is the shortest meaningful interval in current physics, the timescale below which our understanding of space-time probably breaks down. The Planck mass is approximately 2.176 times 10 to the negative 8 kilograms, about 22 micrograms, roughly the mass of a small grain of sand or a few human cells. This seems modest compared to the extremity of Planck length and time, but relative to particle masses, it is enormous. A proton has a mass of about 1.67 times 10 to the negative 27 kilograms. The Planck mass is about 10 to the 19 times larger, the same ratio as the Planck length to a proton. The Planck density combines these into a density scale. The Planck mass divided by the cube of the Planck length. This gives approximately 5.15 times 10 to the 96 kilograms per cubic meter. For perspective, the density of an atomic nucleus is about 2 times 10 to the 17 kilograms per cubic meter. The Planck density is 80 orders of magnitude higher than nuclear density. A single cubic meter at Planck density would contain more mass than the observable universe, which has a total mass of roughly 10 to the 53 kilograms, spread over a volume of roughly 4 times 10 to the 80 cubic meters. This is the density scale that naive quantum field theory calculations suggest for the vacuum. Let me explain why physicists talk about different cutoff scales, because this affects the precise magnitude of the discrepancy. The Planck scale is the most natural cutoff from a quantum gravity perspective, but it is not the only possibility. Different assumptions about where new physics appears lead to different vacuum energy estimates. If the cutoff is at the electroweak scale, roughly 250 giga-electron volts, or about 4 times 10 to the negative 25 kilograms in mass terms, the predicted vacuum energy is smaller. The electroweak scale is where the Higgs field gives particles their masses, where the weak nuclear force operates. It is the highest energy scale directly probed by current particle accelerators. Using an electroweak cutoff, the predicted vacuum energy density is roughly 10 to the 55 smaller than the Planck prediction. That sounds like a huge reduction, but the observed value is still 10 to the 55 or so times smaller still. The discrepancy shrinks from 120 orders of magnitude to about 55 orders of magnitude, which is somewhat better, but still catastrophic. If the cutoff is at the QCD scale, roughly 200 mega-electron volts, where the strong nuclear force becomes strong and quarks are confined into protons and neutrons, the predicted vacuum energy is smaller yet. The discrepancy becomes roughly 40 to 50 orders of magnitude, depending on details. Even with the lowest reasonable cutoff, corresponding to physics we already understand, the mismatch is at least tens of orders of magnitude. There is no cutoff choice that makes the problem go away. This is important because it shows the vacuum catastrophe is not an artifact of assuming the Planck cutoff. Any reasonable estimate produces a vacuum energy far larger than observed. The 10 to the 120 figure assumes the most extreme but also most natural cutoff. The problem is somewhat less severe with lower cutoffs, but remains enormous. The question is not which cutoff is correct. The question is why all reasonable theoretical estimates, regardless of cutoff, are so much larger than observation. 10 to the 120 is not a number that appears anywhere else in physics. It is not the ratio of any two scales we normally encounter. It is not the number of atoms in the universe, which is roughly 10 to the 80th. It is not the age of the universe in Planck times, which is roughly 10 to the 60. To get a ratio of 10 to the 120, you need to compare something extraordinarily large to something extraordinarily small. And you need to do it twice. Here is one way to think about it. Take the number of atoms in the observable universe, roughly 10 to the 80th. Now square that number. 10 to the 80th times 10 to the 80th is 10 to the 160. The vacuum catastrophe is a mismatch larger than the square of the number of atoms in existence. Another perspective. If you wrote out 10 to the 120 as a standard number with no exponents, you would need 121 digits. That is more than 3 times the number of digits in a Google, which itself has 101 digits. This is not a small error that better calculations might fix. This is not a factor of 2 or 10 that more careful measurements might resolve. This is a disagreement between theory and observation so vast that it challenges whether we understand anything about how quantum mechanics and gravity fit together. Steven Weinberg, one of the most influential physicists of the 20th century, wrote a landmark review of this problem in 1989. He called it the cosmological constant problem and framed it as one of the central puzzles of fundamental physics. In the decades since, the problem has only become more pressing. The discovery of accelerating expansion in 1998 confirmed that the vacuum energy is not zero, which makes the puzzle worse. A zero value might be explained by some unknown symmetry that forces perfect cancellation. A small but non-zero value requires not only nearly perfect cancellation, but a tiny residue left over, fine-tuned to an absurd degree. This is why physicists speak of a catastrophe. The numbers do not work. Something fundamental is missing from our understanding. Let me offer one final analogy for the vacuum catastrophe, because finding new ways to express the problem can help it settle in the mind. Imagine you calculated the temperature of the room you are sitting in using basic thermodynamics. Your calculation gave 10 to the 120 degrees Celsius. You then measured the actual temperature with a thermometer. The reading showed room temperature, roughly 20 degrees Celsius. Your calculation was not slightly wrong. It was wrong by 10 to the 120 degrees. No refinement of your method, no correction for humidity or air pressure could possibly bridge that gap. Something in your theoretical framework must be fundamentally mistaken. This is the position physicists find themselves in with vacuum energy. The theoretical calculation uses well-tested principles of quantum field theory. The observational measurement uses well-tested methods of cosmology. Both seem sound. Yet they disagree by more than 100 orders of magnitude. The solution, whatever it turns out to be, will not be a small adjustment. It will be a reconceptualization of something we thought we understood, either about quantum fields, or about gravity, or about how they combine. Let me trace how physicists came to understand this problem, because the history reveals how unexpected it was. In 1917, just 2 years after publishing General Relativity, Albert Einstein introduced the cosmological constant into his equations. He wanted a static universe, one that neither expanded nor contracted. And the cosmological constant provided the repulsive effect needed to balance gravity. Within a decade, Edwin Hubble's observations showed that the universe was expanding. Einstein's static universe was wrong, and he abandoned the cosmological constant. For decades afterward, most physicists assumed it was exactly zero. The quantum perspective arrived in 1967 and 1968, when the Soviet physicist Yakov Zeldovich pointed out something troubling. Quantum field theory predicted that the vacuum should have non-zero energy. This vacuum energy would behave exactly like Einstein's cosmological constant. If the vacuum energy was as large as naive calculations suggested, it would cause the universe to expand so rapidly that galaxies, stars, and planets could never form. Zeldovich's observation raised the problem clearly. Either the vacuum energy was somehow exactly zero, cancelled by some unknown mechanism, or our understanding of quantum fields and gravity was fundamentally incomplete. In 1989, Steven Weinberg published his comprehensive review, cataloguing the severity of the problem and exploring potential solutions. None of the proposed solutions was satisfactory. The cosmological constant problem entered the mainstream of theoretical physics as one of the hardest unsolved puzzles. The supernova observations changed everything. In 1998 and 1999, 2 independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, announced that distant Type 1a supernovae were fainter than expected. The universe's expansion was not slowing down as gravity should cause. It was speeding up. The simplest explanation was a non-zero cosmological constant, a small but real vacuum energy density that acted as a form of cosmic anti-gravity. The universe was not just expanding, it was accelerating, pushed apart by the energy of empty space. This discovery earned the team leaders the Nobel Prize in Physics in 2011. Let me fill in more historical detail, because the development of these ideas spans a century and involves some of the greatest physicists who ever lived. When Einstein introduced the cosmological constant in 1917, he did not think of it as vacuum energy. He thought of it as a modification to his equations, a new term that could balance gravity and allow a static universe. The physical interpretation, connecting lambda to the energy of empty space, came later. Quantum mechanics emerged in the 1920s, and with it the concept of zero-point energy. Werner Heisenberg's uncertainty principle, published in 1927, implied that quantum systems could not have exactly zero energy in their ground states. The vacuum retained residual fluctuations. Throughout the 1930s and 1940s, physicists developed quantum field theory. The formalism made clear that fields, not particles, were fundamental, and that the vacuum state had specific properties, including non-zero energy. But the gravitational implications were largely ignored. Quantum field theory was developed for particle physics, where vacuum energy did not matter. The connection between quantum vacuum energy and cosmology crystallized in the late 1960s. Yakov Zeldovich, a Soviet physicist who made seminal contributions to both nuclear physics and cosmology, published papers in 1967 and 1968 pointing out the problem explicitly. The quantum vacuum should gravitate. Its energy density should appear in Einstein's equations. The predicted effect should be enormous. Zeldovich's work did not immediately transform the field. Many physicists hoped that some symmetry would force the vacuum energy to zero, eliminating the problem. The cosmological constant was often assumed to be exactly zero in cosmological models of the 1970s and 1980s. Weinberg's 1989 review crystallized the problem for a generation of physicists. He laid out the magnitude of the discrepancy, the various proposed solutions, and why none was satisfactory. His paper became a landmark, framing the cosmological constant problem as one of the deepest puzzles in fundamental physics. The discovery of accelerating expansion in 1998 made the problem unavoidable. The vacuum energy was not zero. It was small, but non-zero. Any solution had to explain not just cancellation, but precise, fine-tuned cancellation, leaving a tiny residue. The supernova results forced physicists to confront the cosmological constant problem in a new way. Before 1998, you could hope that some unknown symmetry set the vacuum energy exactly to zero. Exact cancellation might be strange, but at least it was a single condition that some deep principle might enforce. After 1998, you needed to explain why the vacuum energy was almost zero, but not quite. Not only did the positive contributions from quantum fields need to cancel against something, they needed to cancel with extraordinary precision and leave a tiny remainder, just the right size to cause the observed acceleration. The precision required is absurd. To get the observed vacuum energy from the theoretical prediction, something must cancel 99.999 with 129% of the expected value. This is fine-tuning beyond anything else in physics. Sean Carroll, in a widely read review published in 2001, synthesized the problem for broad physics audiences. He laid out the options clearly. Either we are missing something profound about quantum field theory, or we are missing something profound about gravity, or some combination of both. The observations kept getting better. In 2018 and 2020, the Planck satellite released its final cosmological parameter results. These measurements, combining observations of the cosmic microwave background with other data, provided the most precise constraints yet. According to Planck, dark energy accounts for approximately 68.5% of the total energy density of the universe. The Hubble constant, which describes how fast the universe is expanding, is approximately 67.4 kilometers per second per megaparsec, or about 41.9 miles per second per megaparsec. The equation of state parameter, called W, describes how dark energy's pressure relates to its energy density. For a true cosmological constant, W equals -1 exactly. The observations are consistent with W being very close to -1, supporting the interpretation that dark energy is indeed a cosmological constant, the vacuum energy of empty space. More recently, the Dark Energy Spectroscopic Instrument, or DESI, has been testing whether dark energy might actually vary over time. Some combinations of datasets have shown mild hints that we might deviate slightly from -1, suggesting that dark energy could be evolving. These results are not yet definitive, and the standard cosmological constant remains the simplest model consistent with most data. Let me explain the Lambda-CDM model in more detail, because understanding the standard cosmological model helps frame what the vacuum catastrophe threatens. Lambda-CDM is the simplest model that fits cosmological observations. Lambda refers to the cosmological constant, the vacuum energy density that drives accelerating expansion. CDM stands for cold dark matter, a form of matter that does not interact with light but does interact gravitationally. The model has 6 primary parameters. The first is the density of ordinary baryonic matter, the protons, neutrons, and electrons that make up atoms, stars, and planets. This accounts for about 5% of the total energy density. The second is the density of cold dark matter. This accounts for about 26.5% of the total energy density. We do not know what dark matter is made of, but we know it must exist because galaxies rotate in ways that require more mass than visible matter provides, and because gravitational lensing reveals mass where no luminous matter appears. The third is the dark energy density, the vacuum energy we have been discussing. This accounts for about 68.5% of the total energy density. It dominates the universe today. The fourth is the optical depth to reionization, which describes how much the universe was ionized when the first stars formed. The fifth is the spectral index of primordial fluctuations, which describes how density variations in the early universe depended on scale. The sixth is the amplitude of primordial fluctuations, which sets the overall size of density variations. From these 6 parameters, the model predicts an enormous range of observations. The patterns in the cosmic microwave background, the distribution of galaxies across billions of light years, the expansion rate of the universe at different cosmic epochs, the formation and evolution of cosmic structures. The predictions match observations with remarkable precision. Lambda-CDM is one of the most successful physical theories ever developed, fitting data across vast ranges of scales and times. Yet, Lambda-CDM does not explain why lambda has its particular value. The model takes the vacuum energy density as an input parameter fitted to observations. It does not derive this value from deeper principles. The vacuum catastrophe asks, why is this parameter what it is? Quantum field theory suggests it should be 10 to the 120 times larger. Lambda-CDM works perfectly well regardless of this discrepancy, but it leaves the fundamental question unanswered. Let me describe in more detail how astronomers determined that the universe is accelerating, because this evidence is crucial to establishing that vacuum energy is real. Type 1a supernovae occur when white dwarf stars in binary systems accumulate enough material from their companions to exceed a critical mass and explode. The explosions have remarkably consistent intrinsic brightness, making them useful as standard candles for measuring cosmic distances. By comparing a supernova's apparent brightness to its known intrinsic brightness, astronomers can calculate how far away it is. By measuring the redshift of its light, they can determine how fast the universe was expanding when that light was emitted. Combining distance and redshift for many supernovae traces the expansion history of the universe. In the late 1990s, two teams were competing to map this expansion history. The Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University, with Adam Rees playing a key role, both accumulated enough data to draw conclusions. The expectation was that the expansion should be slowing down. Gravity pulls matter together. As the universe expands, the mutual gravitational attraction of all the matter should act as a brake, gradually decelerating the expansion. The question was how fast the deceleration was occurring. The data showed the opposite. Distant supernovae were fainter than expected for a decelerating universe. They were farther away than they should be if expansion was slowing. The universe's expansion was speeding up, not slowing down. This discovery stunned the physics community. It implied that some form of energy with negative pressure was pushing the universe apart, counteracting gravity's attractive pull. The simplest candidate was vacuum energy, the cosmological constant that Einstein had introduced and then abandoned 8 decades earlier. Subsequent observations confirmed the result. The cosmic microwave background, the afterglow of the Big Bang, carries patterns that encode the universe's composition. The Planck satellite's measurements of these patterns independently pointed to about 68.5% dark energy. Observations of how galaxies cluster, how gravitational lensing bends light around massive objects, how baryon acoustic oscillations appear in the galaxy distribution, all converge on the same picture. Vacuum energy dominates the universe's energy budget and drives accelerating expansion. Let me break down the universe's energy budget more carefully, because the numbers reveal something striking. According to the best current measurements, the universe contains roughly 68.5% dark energy, 26.5% dark matter, and 5% ordinary matter. These percentages refer to the total energy density, which, in general relativity, determines how space-time curves and how the universe expands. Ordinary matter, the atoms that make up stars, planets, and human beings, accounts for only about 5%. Everything you can see, touch, or detect with any instrument that measures ordinary matter is a small minority of the universe's content. Dark matter, which does not emit or absorb light but exerts gravitational attraction, accounts for about 26.5%. We know dark matter exists because galaxies rotate in ways that require more mass than visible matter can provide. Because gravitational lensing reveals mass where no luminous matter exists. Because the patterns in the cosmic microwave background require its presence. We do not know what dark matter is made of, but we know it is there. Dark energy, the vacuum energy we have been discussing, accounts for about 68.5%. It is the majority component. The dominant ingredient of the universe is empty space itself. What makes this strange is that dark energy was once negligible. In the early universe, matter and radiation dominated. The energy density of matter decreases as the universe expands because the same amount of matter spreads over increasing volume. The energy density of radiation decreases even faster because photons lose energy as their wavelengths stretch with expansion. Vacuum energy density, by contrast, stays constant as space expands. New space does not dilute the vacuum energy because new space comes with its own vacuum energy. The cosmological constant is constant. As the universe expanded, matter and radiation diluted while vacuum energy remained steady. Eventually, vacuum energy became the dominant component. This transition happened roughly 5 billion years ago. Since then, the expansion has been accelerating. The coincidence that we live shortly after this transition is sometimes called the coincidence problem. Why do we exist at the particular epoch when dark energy and matter have comparable densities? In the distant past, vacuum energy was negligible. In the distant future, it will completely dominate. We happen to live in the brief window when both matter. Let me explain why vacuum energy causes accelerating expansion rather than gravitational attraction, because this seems counterintuitive at first. In Newtonian gravity, mass attracts mass. More energy means more mass, by Einstein's famous equivalence. You might expect that adding energy to empty space would create more gravitational attraction, slowing the expansion rather than speeding it up. General relativity is more subtle. In Einstein's equations, both energy density and pressure contribute to gravity. Ordinary matter has positive energy density and positive or zero pressure. Both contributions cause attraction. The expansion slows. Radiation has positive energy density and positive pressure, equal to 1/3 the energy density. Both contributions cause attraction, though the pressure contribution is significant. The expansion slows even faster in a radiation-dominated universe than in a matter-dominated one. Vacuum energy is different. It has positive energy density but negative pressure. In fact, for a cosmological constant, the pressure is exactly negative the energy density. In general relativity, the gravitational effect of pressure is 3 times the gravitational effect of energy density. For vacuum energy, the positive energy density contributes attraction, but the negative pressure, 3 times larger in its gravitational effect, contributes repulsion. The net result is repulsion. Vacuum energy causes expansion to accelerate. This behavior follows from the peculiar nature of vacuum energy. When ordinary matter expands, it does work against pressure, losing energy. When radiation expands, it loses energy as wavelengths stretch. Vacuum energy does neither. As space expands, the vacuum energy density stays constant. because new space brings new vacuum energy. The total vacuum energy increases as the universe grows. This constancy requires negative pressure. Thermodynamically, the work done during expansion must equal the change in energy. If the energy increases while volume increases, the pressure must be negative. The negative pressure is not something you can feel directly. It is not like suction. It is a property of how vacuum energy couples to gravity, causing the fabric of space-time to expand faster and faster. Let me discuss the equation of state parameter in more detail, because it tells us whether dark energy is truly a cosmological constant or something else. The equation of state parameter, called W, relates the pressure of a substance to its energy density. For a cosmological constant, W equals exactly -1. The pressure is exactly negative the energy density. Other forms of dark energy would have different values of W. A scalar field slowly rolling down a potential, sometimes called quintessence, would typically have W between -1 and -1/3. A phantom energy would have W less than -1, corresponding to even more rapid acceleration and eventually a big rip scenario where expansion tears apart all structures. Measuring W precisely matters greatly. If observations show W equals -1 with high precision, dark energy is likely a cosmological constant. If W deviates from -1, dark energy is dynamical, something more complicated than simple vacuum energy. The Planck satellite's measurements, combined with other cosmological data, constrain W to be very close to -1. The central value is consistent with -1, and the uncertainties allow only small deviations. More recent measurements, including those from DESI, have probed whether W might vary over cosmic time. If dark energy evolves, W could be different at different epochs. Some datasets have shown mild hints of such evolution, but the significance is not yet high enough to draw firm conclusions. The precision achieved is remarkable. We are measuring the equation of state of empty space across billions of light years and billions of years of cosmic history. The fact that we can constrain W at all demonstrates the power of modern observational cosmology. If future observations firmly establish that W differs from -1, the vacuum catastrophe would take on a different character. The problem would no longer be why the cosmological constant is so small, but why dark energy has the particular dynamical properties it does. The 10 to the 120 discrepancy might remain, or new physics might reframe it entirely. Let me describe what the future holds for dark energy research, because new observations may transform our understanding. DESI continues collecting data. By the time it completes its survey, it will have mapped the three-dimensional positions of tens of millions of galaxies and quasars. This unprecedented map will trace the expansion history of the universe with precision far exceeding current measurements. If dark energy evolves over time, DESI may detect that evolution definitively. The Vera Rubin Observatory, under construction in Chile, will survey the entire visible sky repeatedly over 10 years. Its legacy survey of space and time will detect millions of Type Ia supernovae, vastly more than current samples. The statistical power will enable much tighter constraints on the expansion history. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will combine supernova measurements with weak gravitational lensing observations. Weak lensing measures how the gravity of intervening matter distorts the shapes of distant galaxies. This probes both the expansion history and the growth of cosmic structure, providing independent constraints on dark energy. The Euclid Space Telescope, launched by the European Space Agency, is already collecting data. It will survey a large fraction of the sky, measuring galaxy positions and shapes to constrain dark energy through multiple methods simultaneously. These observatories will test whether dark energy is truly a cosmological constant or something else. They will measure W with percent-level precision. They will search for variation of W over cosmic time. They will look for any deviation from the standard Lambda-CDM model. If all observations confirm W equals -1 with high precision across cosmic history, the simplest interpretation is a true cosmological constant. The vacuum catastrophe would remain. Why is this constant so much smaller than quantum field theory predicts? If observations reveal that W differs from -1 or varies over time, dark energy would be dynamical. New theories would be needed to explain its properties. The vacuum catastrophe might be reframed or might point toward entirely different physics. Either outcome advances understanding. The observations narrow the possibilities and guide theoretical development. Let me discuss what experimental tests might shed light on the vacuum catastrophe, because the problem is not purely theoretical. The most direct tests come from cosmological observations. Measuring the expansion history of the universe more precisely constrains the properties of dark energy. If dark energy truly is a cosmological constant, W equals -1 exactly at all times. Any deviation would indicate dynamical dark energy, which would require new physics beyond the standard model. Current measurements constrain W to be very close to -1, but uncertainties remain. The Planck satellite, DESI, the Vera-Rubin Observatory, the Roman Space Telescope and Euclid will all improve these constraints. Percent-level precision on W is achievable within the next decade. Tests of gravity at short distances also probe vacuum energy indirectly. If vacuum energy behaves differently at small scales, precision measurements of gravitational forces might reveal anomalies. Torsion balance experiments have tested gravity down to sub-millimeter scales without finding deviations from general relativity. The Casimir Effect provides another experimental handle. Precise measurements of Casimir forces test our understanding of vacuum fluctuations in quantum electrodynamics. Any unexpected behavior could hint at new physics affecting vacuum energy. Particle physics experiments at the Large Hadron Collider search for new particles that might affect vacuum energy contributions. Discovering supersymmetric partners, if they exist, would reveal the scale of supersymmetry breaking and constrain how much cancellation supersymmetry can provide. Gravitational wave observations probe strong field gravity in ways previously impossible. Merging black holes and neutron stars test general relativity in extreme conditions. Any deviations could indicate modifications to gravity that might relate to the cosmological constant. Problem: none of these experiments directly measures the discrepancy between quantum field theory predictions and observations. The 10 to the 120 ratio is not something you can check with a single experiment. What these measurements do is constrain the possibilities, narrowing the space of theories that might resolve the vacuum catastrophe. Progress may come from unexpected directions. History shows that fundamental problems are often solved by ideas that seem unrelated at first. The solution to the vacuum catastrophe might emerge from developments in quantum information, condensed matter physics, or mathematical frameworks not yet applied to cosmology. I want to shift now to something remarkable, a situation where vacuum energy produces a measurable force right here on Earth, in laboratory experiments that you can actually perform. This is the Casimir Effect, and it demonstrates that empty space is not as empty as it seems. In 1948, the Dutch physicist Hendrik Casimir predicted something strange. Take two electrically conducting plates, perfectly flat and parallel, and bring them very close together in a vacuum. Casimir calculated that the plates would experience a small but measurable attractive force, pulling them toward each other. The force does not come from electric charges. The plates are electrically neutral. It does not come from magnetism or from any classical field. It comes from the vacuum itself. The explanation involves the quantum fluctuations of the electromagnetic field. In empty space, the electromagnetic field is in its ground state, with 0-point fluctuations at all wavelengths. These fluctuations exist everywhere, filling all of space. When you introduce two conducting plates, you change the boundary conditions. The electromagnetic field must satisfy certain requirements at the plate surfaces. This restriction eliminates some of the possible fluctuation modes between the plates, while leaving the modes outside unchanged. The result is that there are fewer vacuum fluctuations between the plates than outside. The vacuum energy density between the plates is slightly lower than the vacuum energy density outside. This difference in energy density produces a pressure that pushes the plates together. The force is tiny at human scales. The predicted pressure depends very sensitively on the separation between the plates, scaling as the inverse fourth power of the distance. Double the separation, and the pressure drops by a factor of 16. Reduce the separation by half, and the pressure increases 16-fold. For plates separated by 1 micrometer, about 1/millionth of a meter, or roughly 1/100th the width of a human hair, the predicted pressure is approximately 0.0013 pascals. That is far below atmospheric pressure, which is about 101,325 pascals. You would never notice such a tiny force in everyday situations. At 100 nanometers separation, 1/10th of a micrometer, the pressure rises to approximately 13 pascals. Over a 1 square meter area, that would correspond to about 13 newtons of force, roughly the weight of 1.3 kilograms on Earth. Let me provide more detail on the physics of the Casimir effect, because it illustrates how vacuum energy manifests in measurable ways. Hendrik Casimir was working at Philips Research Laboratories in the Netherlands when he made his prediction in 1948. He was trying to understand forces between colloidal particles, and his colleague Dirk Polder had been working on van der Waals forces between molecules. Casimir's insight was to calculate the effect of altered vacuum fluctuations between conducting surfaces. The electromagnetic field in empty space can oscillate at any wavelength. Near a conducting surface, the field must satisfy boundary conditions. The electric field component parallel to the surface must vanish at the conductor. This requirement restricts which oscillation modes are allowed. Between two parallel conducting plates, both surfaces impose boundary conditions. Only certain wavelengths fit properly. The field must have nodes, points of zero oscillation at both surfaces. This restricts the allowed modes to a discrete set, like the standing waves on a guitar string that must have fixed endpoints. Outside the plates, no such restriction exists. All wavelengths are allowed. The vacuum fluctuations outside include modes that are forbidden inside. Because there are fewer modes inside, the vacuum energy density inside is lower than outside. This difference in energy density creates a pressure difference. The vacuum outside pushes harder than the vacuum inside. The plates feel a net attractive force pushing them together. The force depends sensitively on the plate separation, because the restriction on allowed modes depends on separation. Closer plates forbid more modes, increasing the energy density difference and with it the force. Casimir's original calculation assumed perfectly conducting plates at absolute zero temperature. Real experiments involve imperfect conductors at finite temperature, which complicates the calculation. The theory must account for the actual electromagnetic response of the plate materials, which varies with frequency. Despite these complications, the experiments by Lamoureux in 1997 and Mohideen and Roy in 1998 confirmed the basic prediction. The measured forces matched theoretical calculations that included realistic material properties. The vacuum fluctuations are real, and their effects are measurable. For decades after Casimir's 1948 prediction, precise measurements remained elusive. The forces are small, the required separations are tiny, and controlling all the experimental complications proved extraordinarily difficult. The breakthrough came in 1997, when Steve Lamoureux at the University of Washington used a torsion pendulum to measure Casimir forces between surfaces separated by 0.6 to 6 micrometers. His results agreed with theoretical predictions, providing the first high-precision confirmation of the Casimir effect. The following year, in 1998, Umar Mohideen and Anushree Roy used an atomic force microscope to measure Casimir forces at even smaller separations, between 0.1 and 0.9 micrometers. Their results also matched theory, extending the confirmation to the submicron regime, where the forces are larger and the quantum nature of the effect is more pronounced. These experiments demonstrated something remarkable. The vacuum has measurable physical consequences. Empty space, cleared of all matter and radiation, still exerts forces on objects placed within it. The zero-point fluctuations predicted by quantum field theory are not just mathematical abstractions. They produce effects that show up in careful laboratory measurements. The Casimir effect is one of those rare situations where you can point to a tabletop experiment and say, even empty space has measurable physical properties. Think about what that means. We usually imagine empty space as nothing, as the absence of everything, as the background against which things happen. The Casimir effect shows that empty space is something, a quantum medium with specific characteristics, specific energies, specific effects on matter. This same vacuum energy that produces the Casimir force between laboratory plates is, according to quantum field theory, present everywhere in the universe. The question that haunts theoretical physics is why this vacuum energy does not gravitate with the strength that calculations predict. The Casimir effect confirms that vacuum fluctuations are real. Cosmological observations confirm that the vacuum has some energy that drives cosmic acceleration. The mystery is why the number linking these two phenomena is so absurdly small. Let me return to the Casimir effect and explore the physics more carefully, because it illustrates something important about how vacuum energy manifests. The formula for the ideal Casimir pressure between two perfectly conducting parallel plates at absolute zero temperature is elegant. The pressure depends on Planck's constant, the speed of light, and the separation between the plates raised to the fourth power. This inverse fourth power scaling is crucial. It means the Casimir force is extraordinarily sensitive to distance. Reduce the plate separation by a factor of 10, and the pressure increases by a factor of 10,000. At 1 micrometer separation, about 3.28 times 10 to the negative 6 feet, the predicted pressure is approximately 0.0013 pascals, or about 1.89 times 10 to the negative 7 pounds per square inch. This is negligible by everyday standards. At 100 nanometers separation, 10 times smaller, the pressure jumps to approximately 13 pascals, or about 1.89 times 10 to the negative 3 pounds per square inch. Still small compared to atmospheric pressure, but measurable with precision instruments. The steep scaling explains why the Casimir effect is irrelevant at human scales, but becomes significant at the nanometer level. Two books sitting on a shelf do not snap together due to Casimir forces because their separation, however small it looks to us, is billions of times larger than the distances where Casimir effects become appreciable. At the nanoscale, where engineers build devices with components separated by tens or hundreds of nanometers, Casimir forces cannot be ignored. They affect the design of micro-electromechanical systems and pose challenges for nanotechnology. The vacuum itself pushes on components at these scales. This scaling also explains why measuring the Casimir effect required such painstaking experimental work. You need surfaces that are extremely flat, positioned with nanometer precision in environments where other forces like electrostatic attraction have been carefully eliminated. The experiments that confirmed Casimir's prediction in 1997 and 1998 were technical tours de force. The success of these experiments is a reminder that quantum field theory, for all its mathematical abstractness, describes real physics. The vacuum fluctuations are not just theoretical constructs, they produce measurable effects when you know where to look. Let me consider what the vacuum catastrophe means for everyday life, because surprisingly it connects to practical concerns. In nanotechnology, the Casimir effect is not a curiosity but a design constraint. Engineers building micro-electromechanical systems must account for vacuum forces between components. At separations below a few hundred nanometers, Casimir forces can cause moving parts to stick together, a phenomenon called stiction. The vacuum itself interferes with mechanical operation. The inverse fourth power scaling makes Casimir forces extremely sensitive to separation. Two surfaces that work fine at one separation may snap together if brought slightly closer. This limits how small mechanical devices can be made. The vacuum sets boundaries on engineering. Some researchers have explored whether Casimir forces could be harnessed for useful purposes. Could you build actuators powered by vacuum fluctuations? Could you design surfaces that repel rather than attract due to specific material properties? The physics allows such possibilities in principle, though practical applications remain elusive. The connection to cosmology is more philosophical than practical. The accelerating expansion driven by vacuum energy will not affect Earth or the solar system for billions of years. Gravitational binding holds local structures together against the cosmic acceleration. Galaxies will not fly apart. The solar system will not disperse. What will happen over extremely long timescales is that distant galaxies will accelerate away faster than light can travel, crossing beyond our cosmic horizon. The observable universe will shrink. Eventually, billions of years from now, observers in our galaxy will see only local structures. The wider universe will have vanished behind the horizon of accelerating expansion. This fate is not certain. It depends on whether dark energy truly is a cosmological constant, or whether it evolves. If dark energy varies, the long-term future could be different. More observations will constrain the possibilities. For now, the practical relevance of the vacuum catastrophe is limited to advanced nanotechnology on one hand and questions about the ultimate fate of the cosmos on the other. Between these extremes lies everyday life, blissfully unaffected by the quantum weirdness of empty space. Let me be more precise about why the numbers do not match, because the details reveal the depth of the problem. In quantum field theory without gravity, the absolute value of vacuum energy does not matter. You can add or subtract any constant from the energy, and all the physics stays the same. Experiments measure energy differences, transitions between states, forces between objects. The baseline energy cancels out. This is called renormalization. Quantum field theory calculations often produce infinite answers, and renormalization is the mathematical procedure that extracts finite, physically meaningful results. Part of this procedure involves setting the vacuum energy to zero by definition. In non-gravitational physics, this works perfectly well. General relativity does not allow this freedom. In Einstein's equations, all energy gravitates. The vacuum energy is not just a baseline, it is a source term that curves space-time. You cannot simply define it away. This tension lies at the heart of the cosmological constant problem. Quantum field theory says vacuum energy can be renormalized to any convenient value. General relativity says the actual value matters and affects the expansion of the universe. The two frameworks are incompatible on this point. One possibility is that different contributions to the vacuum energy cancel against each other's. Quantum fields come in different types, bosons and fermions, and they contribute to the vacuum energy with opposite signs in certain theories. Perhaps these contributions nearly cancel, leaving only a tiny residue. The problem is that the cancellation must be almost perfect. To match observations, positive and negative contributions totaling roughly 10 to the 113 joules per cubic meter must cancel down to 10 to the negative 10 joules per cubic meter. That requires cancellation to 122 decimal places. No known symmetry enforces such precise cancellation. Supersymmetry, a proposed extension of particle physics, would require exact boson-fermion matching. But supersymmetry, if it exists, is clearly broken in our universe. The known particles do not have superpartners of equal mass. Whatever residual cancellation supersymmetry might provide, it is nowhere near sufficient. Let me explain why supersymmetry was once hoped to solve the vacuum catastrophe, and why it does not. Supersymmetry is a proposed extension of the standard model of particle physics that relates bosons, particles with integer spin like photons, to fermions, particles with half-integer spin like electrons. In a supersymmetric theory, every known particle would have a superpartner with different spin but otherwise similar properties. The relevance to vacuum energy is that bosons and fermions contribute with opposite signs. Boson fields add positive zero-point energy. Fermion fields add negative zero-point energy. If supersymmetry were exact, with every boson having a fermionic partner of exactly equal mass, the contributions would cancel perfectly. The vacuum energy would be zero. This was a beautiful possibility. Supersymmetry could solve the vacuum catastrophe by enforcing exact cancellation through a symmetry principle. Zero vacuum energy would be natural, not fine-tuned. The problem is that supersymmetry, if it exists, is not exact. We have not observed superpartners at particle accelerators. The electron does not have a bosonic partner of equal mass. Neither does any other known particle. If superpartners exist, they must be much heavier than their ordinary counterparts. Broken supersymmetry still provides some cancellation, but not nearly enough. When supersymmetry is broken at some energy scale, the remaining vacuum energy is proportional to that scale raised to the fourth power. Even if supersymmetry is broken at the electroweak scale, the residual vacuum energy is still about 10 to the 55 times larger than observed. Higher breaking scales give worse discrepancies. If supersymmetry is broken at the Planck scale, you recover the full 10 to the 120 problem. Supersymmetry alone cannot explain the observed vacuum energy unless it is broken at an extremely low scale, far below what particle physics experiments suggest. The Large Hadron Collider has searched for superpartners without finding them. This pushes the breaking scale higher, making supersymmetry less effective as a solution to the vacuum catastrophe. The symmetry that was supposed to help seems unable to do so given current constraints. Physicists have proposed many approaches to the cosmological constant problem. None has achieved broad acceptance. Some proposals invoke new symmetries that might force the vacuum energy to be small or zero. These approaches struggle to explain why the energy is small but not exactly zero, as observations require. Some proposals involve modifying gravity itself. Perhaps general relativity is incomplete, and a more comprehensive theory of gravity would treat vacuum energy differently. These approaches face the challenge of reproducing the many successful predictions of general relativity while altering its behavior specifically for vacuum energy. Some proposals invoke the landscape of string theory, the idea that there might be an enormous number of possible universes with different vacuum energies. In this view, we live in a universe where the vacuum energy happens to be small, because only in such universes can galaxies, stars, and observers exist. This is an anthropic argument. The vacuum energy is small not because of any fundamental mechanism, but because we could not exist to ask the question if it were large. The anthropic approach troubles many physicists because it abandons the search for a dynamical explanation. It says the answer is selection bias, not physics. We observe a small vacuum energy because we are here to observe it, and we could only be here if the vacuum energy were small. This may be true, but it feels unsatisfying as a final answer. Jérôme Martin published a detailed review in 2012 examining the cosmological constant problem from multiple angles. He catalogued the various proposals, the difficulties each faces, and the precise sense in which the problem remains unsolved. The magnitude estimates depend on assumptions about cutoff scales and renormalization conventions. But under any reasonable approach, the mismatch is severe. The problem remains open. More than a century after Einstein introduced the cosmological constant, more than half a century after Zeldovich connected it to quantum vacuum energy, more than 3 decades after Weinberg's landmark review, we still do not know why empty space weighs so little. This is not a failure of physics. It is a signpost pointing toward physics we have not yet discovered. Let me discuss modified gravity approaches, because some physicists believe the vacuum catastrophe points to problems with general relativity itself. General relativity is extraordinarily well tested in the solar system and in binary pulsar systems. It predicts the precession of Mercury's orbit, the bending of starlight by the Sun, the gravitational redshift of clocks, and the emission of gravitational waves from merging black holes. All these predictions match observations. Yet, general relativity has been tested primarily in relatively weak gravitational fields and at relatively small scales compared to the cosmos. Perhaps it breaks down at cosmic scales or when vacuum energy is involved. Modified gravity theories alter Einstein's equations in ways designed to avoid or reduce the vacuum catastrophe. Some theories include additional fields that couple to gravity. Some theories modify how gravity responds to vacuum energy specifically. Some theories change the structure of space-time at very large scales. The challenge for any modified gravity theory is to reproduce the successes of general relativity where it has been tested, while changing its predictions in the cosmological regime. This is a narrow target. Most simple modifications either spoil the agreement with solar system tests or fail to address the vacuum catastrophe. A class of theories called degravitation proposes that vacuum energy gravitates differently from ordinary energy, that its gravitational effect is somehow suppressed. If true, the enormous theoretical vacuum energy might exist, but simply not curve space-time as much as general relativity predicts. These ideas remain speculative. No modified gravity theory has achieved broad acceptance as a solution to the vacuum catastrophe. The problem is that the required modification is extreme. You need to suppress the gravitational effect of vacuum energy by 120 orders of magnitude, while leaving other predictions unchanged. General relativity's simplicity and elegance resist modification. Adding complexity to solve the vacuum catastrophe risks introducing new problems. Most physicists suspect the solution lies elsewhere, perhaps in quantum gravity rather than classical modifications. Let me explore the anthropic argument more carefully, because it represents one serious approach to the vacuum catastrophe. The anthropic argument starts with an observation. If the vacuum energy were much larger than observed, the universe would be very different. A large, positive vacuum energy would cause space to expand so rapidly that matter could never clump into galaxies. Stars would not form, planets would not form, life would not arise. Observers would not exist to measure the vacuum energy. A large negative vacuum energy would cause the universe to collapse before stars and galaxies could form. Again, no observers. Only in a narrow range of vacuum energies can complex structures develop and persist long enough for life to arise. We observe a small vacuum energy because we could only exist to make observations if the vacuum energy were small. This argument does not explain why the vacuum energy has its specific value. It explains why we should not be surprised to find ourselves in a universe with that value. Selection bias replaces dynamical explanation. For the anthropic argument to work, there must be many regions of reality with different vacuum energies. String theory provides one framework for this. The landscape of string theory contains an enormous number of possible vacuum states, each with different properties. Different regions of a multiverse might occupy different vacuum states. If the multiverse is real, and if vacuum energies vary across it, the anthropic explanation becomes plausible. We live in a hospitable patch simply because inhospitable patches have no observers. Many physicists find this unsatisfying. It abandons the search for a fundamental mechanism that determines the vacuum energy. It says the answer is environmental, not fundamental. It replaces why with where. Others argue that anthropic reasoning is perfectly scientific. If the conditions for observation are highly restrictive, selection effects are real and must be accounted for. The anthropic explanation may be the correct one, even if it feels less satisfying than a dynamical mechanism. The debate continues. Without a complete theory of quantum gravity, and without evidence for or against the multiverse, the anthropic explanation can neither be confirmed nor ruled out. Let me speculate about what a resolution of vacuum catastrophe might look like, because understanding the shape of a solution helps frame the problem. One possibility is that the naive calculation is simply wrong, that we have made an error in how we compute vacuum energy. Perhaps quantum field theory should not be applied to the vacuum in the way we assume. Perhaps the sum over modes that gives the enormous prediction is physically meaningless, a mathematical artifact rather than a real contribution to gravity. This possibility is hard to square with the Casimir effect, which seems to confirm that vacuum fluctuations are real and have measurable consequences. Any resolution that discards vacuum energy entirely would need to explain Casimir forces in some other way. A second possibility is that vacuum energy is real, but does not gravitate in the usual way. General relativity might be incomplete when applied to vacuum energy specifically. A more complete theory might include mechanisms that suppress or cancel the gravitational effect, while leaving other predictions unchanged. A third possibility is that cancellations between different contributions reduce the vacuum energy to its observed small value. This is the supersymmetry approach generalized. Perhaps some deeper symmetry, one we have not yet discovered, enforces near-perfect cancellation. The 120-digit precision seems absurd, but nature might have symmetries we cannot yet imagine. A fourth possibility is the anthropic explanation. If the vacuum energy varies across a multiverse, selection effects explain why we observe a small value. This would mean the vacuum catastrophe is not really a problem to be solved, but a selection effect to be understood. A fifth possibility is that new physics at the quantum gravity scale changes the rules entirely. Perhaps space-time is discrete at very small scales. Perhaps the notion of continuous fields breaks down. Perhaps the vacuum itself is fundamentally different from what quantum field theory describes. Each possibility points in a different direction. Some require modifications to quantum field theory. Some require modifications to gravity. Some require accepting selection effects. Some require entirely new frameworks. The resolution, when it comes, will likely transform our understanding of either quantum mechanics, gravity, or both. Problems this severe do not have minor solutions. Let me offer some more ways to feel the scale of this problem, because numbers like 10 to the 120 are hard to absorb. The Planck scale sets the natural units for quantum gravity. The Planck length is approximately 1.616 times 10 to the negative 35 meters, or about 5.3 times 10 to the negative 35 feet. This is incomprehensibly small. A proton is about 10 to the 20 times larger than the Planck length. The ratio of a proton to a Planck length is roughly the same as the ratio of the observable universe to a proton. The Planck mass is approximately 2.176 times 10 to the negative 8 kilograms, or about 4.8 times 10 to the negative 8 pounds. This is small by everyday standards, about the mass of a grain of sand, but it is enormous compared to elementary particles. The Planck mass is about 10 to the 19 times larger than a proton mass. When you calculate the Planck density, dividing the Planck mass by the cube of the Planck length, you get approximately 5.15 times 10 to the 96 kilograms per cubic meter. This is the natural density scale suggested by quantum gravity. 1 cubic meter of space at Planck density would weigh more than the entire observable universe. The observed vacuum energy density is about 5.89 times 10 to the negative 27 kilograms per cubic meter. That is 122 orders of magnitude smaller than the Planck density. To visualize the gap differently, imagine you had a cube 1 meter on a side, filled with vacuum at the theoretically predicted density. Now imagine a cube containing the observed vacuum energy. To match the volumes, you would need the second cube be vastly, almost unimaginably larger. Or you would need to accept that the energy in the first cube had been reduced by a factor of 10 to the 122. Neither picture really captures the absurdity. The numbers are beyond human intuition. They sit outside any physical comparison we can make. This is why the vacuum catastrophe occupies a special place in theoretical physics. It is not just a discrepancy. It is a sign that something is deeply wrong with how we combine our best theories. Let me try one more approach to making the scale of the problem visceral, because 10 to the 120 defeats ordinary imagination. Imagine you had $100 trillion. That would make you incomprehensibly wealthy, richer than all the billionaires on Earth combined many times over. Now imagine someone came to you and said, "Your wealth is off by a factor of 10 to the 120 from what it should be." To reach the correct amount, you would need to multiply your 100 trillion by a number so large that writing it out would fill more pages than exist in all the libraries on Earth. The correction dwarfs your original wealth the way the universe dwarfs an atom. Or consider time. The age of the universe is about 13.8 billion years, roughly 4.4 times 10 to the 17 seconds. A Planck time is about 5.4 times 10 to the negative 44 seconds. The ratio of the universe's age to the Planck time is about 8 times 10 to the 60. That ratio, enormous as it is only 10 to the 60. The vacuum catastrophe involves a ratio of 10 to the 120, which is that ratio squared. The mismatch between predicted and observed vacuum energy is like comparing the age of the universe to the Planck time and then doing that comparison again. Another angle. The number of particles in the observable universe is about 10 to the 80. If you took that number and squared it, you would get 10 to the 160, still larger than the vacuum catastrophe ratio, but in the same general regime. The vacuum catastrophe is a mismatch comparable to squaring the number of particles in existence. Numbers this large have no analogue in human experience. We have words for them, we can write them down, but we cannot feel them the way we feel 10 or 100. They exceed intuition. The vacuum catastrophe is not just a problem in physics, it is a confrontation with the limits of human understanding. We have discovered something our minds cannot fully grasp. a discrepancy so vast that it sits outside all normal frames of reference. The problem is not that we lack the mathematics. The problem is that we lack a framework in which the numbers make sense. Let me address some common misconceptions about vacuum energy, because the topic is often oversimplified in popular accounts. You may have heard that the vacuum is full of virtual particles, constantly popping in and out of existence. This picture is evocative but misleading. In quantum field theory, virtual particles are mathematical objects that appear in perturbation theory, the technique physicists use to calculate how particles interact. They are internal lines in Feynman diagrams, a bookkeeping device for organizing calculations. They do not pop in and out of existence in any literal sense. The vacuum is not a foam of transient particles appearing and vanishing. The vacuum is better described as a quantum state with specific correlations and fluctuations. Different measurement procedures probe different aspects of this state. The Casimir effect, for instance, arises from how boundary conditions alter the field correlations between the plates. It does not require thinking about particles popping in and out. Another misconception concerns the Casimir effect itself. Some popular accounts suggest that the Casimir effect proves there is free energy in the vacuum, extractable for useful work. This is incorrect. The Casimir force arises from changes in boundary conditions. You can extract work by letting the plates move together, but this is not free energy. You did work to set up the plates in the first place, and the total energy budget balances. The vacuum is not a battery you can discharge to power machines. A third misconception is that dark energy is a mysterious new force or substance filling space. In the simplest interpretation, dark energy is just the energy of empty space, the vacuum energy that quantum field theory predicts should exist. What is mysterious is not the existence of vacuum energy, but its magnitude. We expected much more. We observe much less. These misconceptions matter because they can lead to confused thinking about what the vacuum catastrophe actually means. The problem is not whether vacuum energy exists. The problem is why its magnitude is so vastly different from theoretical expectations. I want to share something about how I came to understand the vacuum catastrophe, because the path to grasping it taught me something about the nature of physics itself. When I first encountered the 10%, the 120 number in a textbook, my reaction was disbelief. Surely there was a mistake somewhere. Surely someone had made an error in the calculation, or the observations were wrong, or the comparison was being made incorrectly. I spent weeks looking for the flaw. I read Weinberg's original review from 1989. I worked through Sean Carroll's article from 2001. I looked at Jérôme Martin's detailed treatment from 2012. Each source confirmed the same basic picture. The calculation is straightforward. The observation is robust. The discrepancy is real. What finally helped me accept the magnitude of the problem was thinking about it historically. Quantum field theory developed in the 1930s and 1940s, achieving spectacular successes in predicting particle interactions. General relativity developed in 1915 and 1916, achieving spectacular successes in predicting gravitational phenomena. Both theories were tested and confirmed countless times. For decades, physicists used these theories in parallel. Quantum field theory for particle physics, general relativity for gravity and cosmology. The domains did not overlap much. You did not need to worry about quantum vacuum energy when calculating gravitational lensing. You did not need to worry about space-time curvature when calculating particle scattering. The vacuum catastrophe emerges precisely where these two theories meet. It is not a problem within either theory. It is a problem that appears only when you try to connect them. Quantum field theory tells you about vacuum energy. General relativity tells you that vacuum energy gravitates. Together, they give an answer that contradicts observation by 120 orders of magnitude. This helped me understand the problem not as a failure, but as a signpost. The discrepancy marks the edge of our current knowledge. It shows where our two best theories do not fit together. It points toward physics we have not yet discovered. The history of science contains many such signposts. Ultraviolet catastrophe in black-body radiation led to quantum mechanics. The failure of Newtonian mechanics at high speeds led to special relativity. Each contradiction between theory and observation revealed missing physics. The vacuum catastrophe may be the signpost for the next revolution. When I first learned about the vacuum catastrophe, I had to sit with the numbers for a long time before they felt real. 10 to the 120 does not fit in the mind. You can say it, you can write it, but you cannot visualize it in the way you can visualize 10 or 100 or even 1,000,000. The number is too large for intuition. What helped me was thinking about it as a hierarchy of failures. First, there is the raw calculation. You sum up the zero-point energies of quantum field modes, apply a reasonable cutoff, and get a huge number. This part is straightforward quantum mechanics, nothing exotic. Second, there is the observation. You look at how the universe expands, measure the cosmic microwave background, map the distribution of galaxies, and infer the actual vacuum energy density. This part is observational cosmology, built on decades of careful measurements. Third, there is the comparison. The calculation gives one number. The observation gives another. The ratio between them is 10 to the 122. Each step is solid. The calculation follows from quantum field theory, which has been tested in countless experiments. The observation follows from cosmological measurements, which have been refined by multiple independent techniques. The comparison is just arithmetic. Yet the result is absurd. Something in our understanding is fundamentally wrong. This is what makes the vacuum catastrophe fascinating rather than merely frustrating. It tells us that our two best theories, quantum field theory and general relativity, do not fit together in the way we assumed. Somewhere in the combination, an error lurks, and finding that error would likely reveal something profound about how reality works. The problem has resisted solution for decades, despite the efforts of brilliant physicists. This does not mean it is unsolvable. It means we are missing something, some principle or symmetry or framework that we have not yet discovered. That missing piece might be the key to quantum gravity itself. There is something strange about how the same concept, vacuum energy, appears at such different scales. In the laboratory, you measure Casimir forces between plates separated by fractions of a micrometer. The apparatus sits on a table. The measurements take hours or days. The forces involved are tiny but detectable with precision instruments. In cosmology, you measure dark energy through the expansion history of the universe. The distances involved are billions of light years. The measurements span the age of the cosmos. The effects are enormous, driving the accelerating expansion of everything. Both phenomena trace back to the same underlying physics, the energy of empty space. The vacuum that produces Casimir forces between laboratory plates is the same vacuum that fills the cosmos and causes galaxies to accelerate away from each other. Yet, the numbers connecting these phenomena are bizarre. When you zoom from nanometer gaps to billions of light years, from laboratory experiments to cosmic evolution, the same underlying concept keeps reappearing. The vacuum is not nothing. It has properties, it has energy, it affects physical systems. What we cannot explain is why its gravitational effects are so much smaller than its quantum properties would suggest. This is the part that still puzzles me, even after years of studying this. The Casimir effect works. The calculations match the measurements. Quantum field theory correctly predicts the forces between plates at nanometer separations. Then you ask what those same quantum fields contribute to gravity, and the answer is off by a factor of 10 to the 120. It is as if you had a calculator that gave correct answers for addition and subtraction, but was wrong by 120 orders of magnitude for multiplication. You would conclude that something about how you were using multiplication was fundamentally mistaken. The vacuum catastrophe suggests that something about how we combine quantum field theory with gravity is fundamentally mistaken. The problem spans every scale humans can measure, from nanotechnology to cosmology. Its solution, when we find it, will likely transform our understanding of both. Let me bring this up to date with what physicists have learned most recently. The standard model of cosmology, called Lambda-CDM, treats dark energy as a cosmological constant with a fixed value. Lambda is Einstein's cosmological constant. CDM stands for cold dark matter. Together, they describe a universe where about 68.5% of the energy is dark energy, about 26.5% is dark matter, and about 5% is ordinary matter. This model fits observations remarkably well. The cosmic microwave background, the distribution of galaxies, the expansion rate, all match Lambda-CDM predictions within measurement uncertainties. The simplest interpretation is that dark energy is exactly what the cosmological constant says, a constant vacuum energy density that has remained the same throughout cosmic history. Recent observations have tested this interpretation more stringently. The Dark Energy Spectroscopic Instrument, or DESI, has been mapping the three-dimensional distribution of galaxies and quasars to unprecedented precision. By measuring how galaxies cluster at different distances, corresponding to different times in cosmic history, DESI can test whether dark energy has changed over time. In 2024 and 2025, DESI released analyses comparing a pure cosmological constant, with W equal to -1, against models where dark energy evolves. Some combinations of DESI data with other datasets have shown mild hints that W might be slightly different from -1, suggesting possible evolution. These hints are not yet definitive. The statistical significance is modest, and different choices of which datasets to combine give different results. The pure cosmological constant remains consistent with most data. More observations will be needed to determine whether dark energy truly evolves or whether the hints are statistical fluctuations. If dark energy does evolve, the vacuum catastrophe becomes even more puzzling. A pure cosmological constant could perhaps be explained by some symmetry or cancellation mechanism. A varying dark energy would require a dynamical explanation, something that changes over cosmic time, which would constrain possible solutions even further. The observations continue. The problem remains open. Let me explain why many physicists believe the vacuum catastrophe will only be solved by quantum gravity. Quantum field theory is a theory of matter and forces on a fixed space-time background. You specify the space-time geometry, typically flat Minkowski space or curved space around a massive object, and then you quantize the fields living on that background. The space-time itself is classical. General relativity is a theory of space-time geometry itself. Mass and energy curve space-time, and the curvature of space-time tells matter how to move. But in general relativity, space-time is classical, not quantum. There is no uncertainty principle for geometry, no superposition of different space-time configurations. The vacuum catastrophe arises precisely at the interface between these two theories. You calculate the vacuum energy using quantum field theory, where quantum effects are fundamental. You then ask how this energy affects space-time using general relativity, where quantum effects do not apply to geometry itself. Something in this hybrid approach is inconsistent. Either the quantum calculation is wrong, or the way we couple it to classical gravity is wrong, or both. Resolving inconsistency likely requires a theory where space-time itself is quantum mechanical. String theory attempts to provide such a framework. In string theory, particles are not point-like, but are extended one-dimensional objects, strings. The mathematics of string theory includes gravity automatically and treats space-time quantum mechanically in certain regimes. String theory has a landscape of possible vacuum states, perhaps 10 to the 500 or more different configurations. Each would have different vacuum energy. The anthropic explanation fits naturally. We live in a vacuum state with small energy because only such states allow observers. Loop quantum gravity takes a different approach, quantizing space-time geometry directly. Space is discrete at the Planck scale, made of finite chunks rather than continuous medium. The implications for vacuum energy are still being worked out. Neither string theory nor loop quantum gravity has definitively solved the vacuum catastrophe. Both offer frameworks where the problem might eventually be addressed. Progress requires developing these theories further and finding ways to test them experimentally. Let me step back and consider what the vacuum catastrophe tells us about the nature of physics itself. Quantum field theory is one of the most successful theories in the history of science. It predicts the magnetic moment of the electron to more than 10 decimal places. It underlies the standard model of particle physics, which has been confirmed by countless experiments at accelerators around the world. Every test we can perform confirms quantum field theory's predictions. General relativity is also extraordinarily successful. It predicts gravitational lensing, the bending of light by massive objects, with precision. It predicts gravitational waves, ripples in space-time, which we have now detected directly. It explains the expansion of the universe, the structure of black holes, the behavior of GPS satellites. Every test confirms general relativity's predictions. Each theory, taken separately, is among the most precisely tested frameworks in all of science. When you combine them, asking what happens when quantum vacuum energy gravitates, you get an answer that is wrong by 120 orders of magnitude. This is not a failure of either theory individually. Both theories work perfectly within their domains. The failure occurs at the interface, where quantum mechanics meets gravity, where the zero-point energy of fields becomes a source term in Einstein's equations. The vacuum catastrophe is not just a puzzle within physics. It is evidence that our current framework is incomplete. Some deeper theory, which reduces to quantum field theory in one limit and to general relativity in another, must resolve the discrepancy. This hypothetical deeper theory is often called quantum gravity. Developing it is one of the central goals of theoretical physics. String theory, loop quantum gravity, and other approaches each attempt to provide such a framework, but none has yet succeeded in solving the cosmological constant problem. The vacuum catastrophe is a signpost. It points toward physics we have not yet discovered. Its solution will likely transform how we understand space-time, matter, and the nature of empty space itself. Let me reflect on the philosophical significance of the vacuum catastrophe, because it raises questions beyond physics. The vacuum catastrophe confronts us with the limits of human understanding. We have developed quantum field theory and general relativity, two of the most successful theories in history. And when we combine them in what seems like the most straightforward way, we get an answer that is wrong by 120 orders of magnitude. This is humbling. It suggests that our conceptual framework, despite its enormous success, is missing something fundamental. We can calculate the magnetic moment of the electron to 12 decimal places. We can predict gravitational waves from merging black holes before detecting them. Yet we cannot explain why empty space weighs so little. The problem also raises questions about the nature of scientific explanation. What would it mean to solve the vacuum catastrophe? Would a solution that involves 122-digit cancellations be satisfying? Would an anthropic explanation, which replaces dynamics with selection, count as understanding? Different physicists have different intuitions about what constitutes an acceptable answer. Some seek a deep symmetry that forces the vacuum energy to be zero or nearly zero. Some would accept an anthropic explanation if the multiverse framework were well established. Some hope that quantum gravity will dissolve the problem entirely, revealing that the question was based on incorrect assumptions. The vacuum catastrophe also illustrates how physics progresses. The discovery of accelerating expansion in 1998 did not solve the problem. It made it worse by ruling out the simple possibility that vacuum energy is exactly zero. Progress sometimes means sharpening the questions rather than answering them. Future generations of physicists will likely look back on the vacuum catastrophe as one of the great puzzles of our era. Whether they will have solved it, reframed it, or still be struggling with it remains to be seen. What we know now is that something is wrong. The numbers do not match. Somewhere in our understanding of quantum mechanics, gravity, or their combination, an error lurks. Finding that error is one of the great challenges of fundamental physics. The vacuum catastrophe reveals something remarkable about human knowledge. We have measured the energy density of empty space. Think about what that means. Empty space, by definition, contains nothing. No matter, no radiation, nothing you can see or touch or detect in any ordinary way. Yet we have inferred its properties from observations of distant supernovae, from patterns in the cosmic microwave background, from how galaxies cluster across billions of light years. The observed value, about 5.89 times 10 to the negative 27 kilograms per cubic meter, is far below anything we could measure directly. We deduce it from its effects on the expansion of the universe. We see galaxies accelerating away from each other, and we work backward to the energy that must be pushing them. We have also measured forces produced by vacuum fluctuations. In laboratories, using atomic force microscopes and torsion pendulums, we have detected the Casimir Effect between surfaces separated by fractions of a micrometer. The vacuum, despite containing nothing in the classical sense, exerts measurable pressures on matter. These achievements represent the reach of human understanding. We can probe empty space and find that it is not empty. We can measure effects that have no classical explanation. We can infer properties of the vacuum from observations spanning nanotechnology to cosmology. The fact that these measurements produce a puzzle. The 120 order of magnitude discrepancy does not diminish the achievement. It sharpens it. We have pushed our theories to the point where they break, where they reveal their own incompleteness. This is how science advances. You test your ideas until they fail, and then you learn from the failure. The vacuum catastrophe is not a defeat, it is a challenge. Somewhere in the mismatch between quantum field theory and general relativity lies a clue to deeper physics. Finding that clue will require new ideas, new mathematics, perhaps new experiments we cannot yet imagine. When we find it, we will understand something we do not understand now. Why nothing weighs so little. Let me offer one more perspective on why this problem is so strange. In most of physics, when theory and observation disagree, you can usually figure out what went wrong. Perhaps you made a calculational error. Perhaps you ignored some effect that turned out to be important. Perhaps your measurement had systematic biases you did not account for. The vacuum catastrophe is different. The calculation is straightforward. The observation is robust. The discrepancy is not subtle. Consider what would have to happen for the standard explanation to work. Quantum fields contribute to the vacuum energy. Different fields contribute different amounts with different signs. For bosons, the contribution is positive. For fermions, it is negative. If the universe contained exactly the right mix of fields, the contributions might cancel. Positive terms from one set of fields would balance negative terms from others, leaving a small residue. The problem is that the cancellation must be almost perfect. To get from 10 to the 113 joules per cubic meter down to 10 to the negative 10 joules per cubic meter, you need cancellation to 122 significant figures. Not 2 figures, not 10 figures. 122 figures. Nothing else in physics requires such precise cancellation. The fine-tuning is unprecedented. This is why some physicists invoke anthropic reasoning. Perhaps there are many regions of reality with different vacuum energies. We find ourselves in a region where the vacuum energy is small, because only in such regions can structure form, stars ignite, planets coalesce, and observers exist to ask questions. The anthropic explanation is not satisfying to everyone. It replaces dynamical understanding with selection bias. It says, we are here, so the vacuum energy must be small, without explaining the mechanism that produced the small value. Whether anthropic reasoning is the answer, or whether a deeper dynamical explanation awaits discovery, remains unknown. The question is open, and it may remain open until we understand quantum gravity. Let me bring this exploration to a close by returning to the title. Why does nothing weigh more than everything? In what sense is this true? The straightforward answer is that quantum field theory predicts an enormous vacuum energy density, far exceeding the energy density of all the matter and radiation in the universe. If empty space contained the energy that naive calculations suggest, it would dominate all other contributions by a staggering margin. Nothing, in the sense of empty space, would gravitationally outweigh everything else. The mystery is that observations show the opposite. The actual vacuum energy is tiny. It exists, it drives cosmic acceleration, but it is a mere whisper compared to what theory predicts. This inversion is the heart of the vacuum catastrophe. Theory says nothing should be heavy. Observation says nothing is almost weightless. The ratio between expected and observed is 10 to the 120. That ratio haunts theoretical physics. It appears in no other context. It has no natural explanation in our current framework. It points insistently towards something we do not yet understand. The vacuum catastrophe connects quantum mechanics, the physics of the very small, to cosmology, the physics of the very large. It links laboratory experiments measuring Casimir forces between nanometer-separated plates to observations of galaxies accelerating across billions of light years. It ties the ground state energy of quantum fields to the expansion rate of the universe. These connections are profound. They suggest that the same physics underlies phenomena spanning 40 or more orders of magnitude in scale. They imply that solving the vacuum catastrophe will require understanding how quantum mechanics and gravity fit together at a fundamental level. We do not have that understanding yet. The problem remains unsolved after decades of effort by thousands of physicists. This is not a reason for despair. It is an invitation. Somewhere in the mismatch lies a clue to new physics. Perhaps the most important physics discovery of the coming century. The next time you sit in an empty room, consider what fills it. Not air, though air is there. Not light, though light passes through. Consider the space itself, the vacuum that would remain if you removed everything else. That vacuum is not nothing. It has energy. It has fluctuations. It produces measurable forces on matter at tiny scales. At cosmic scales, it drives the accelerating expansion that will eventually carry distant galaxies beyond our visible horizon. We know this. We have measured it. We have confirmed the predictions of quantum field theory in laboratory experiments and the predictions of cosmology in observations of the universe. What we cannot explain is why the vacuum weighs so little. Quantum mechanics says it should weigh enormously. Cosmology says it weighs almost nothing. The discrepancy, 10 to the 120, is the largest mismatch between theory and observation in all of physics. This mismatch is not a failure of science. It is the edge of current knowledge, the place where our theories reveal their incompleteness. Pushing past this edge will require new ideas, perhaps revolutionary ideas, about how quantum mechanics and gravity combine. When those ideas arrive, we will understand something we do not understand now. We will know why nothing is so light, why empty space contributes so little to gravity, despite the enormous zero-point energies that quantum field theory predicts. Until then, the vacuum catastrophe remains one of the great unsolved problems in fundamental physics, a puzzle that connects the smallest scales we can measure to the largest structures in existence. Thank you for taking this journey with me through vacuum energy and cosmological constants, through Casimir forces and cosmic acceleration. These ideas deserve careful attention, and I appreciate you giving them that. If you found this exploration valuable, consider subscribing to the channel. It helps these deep dives reach more curious minds. Sleep well tonight, surrounded by the vacuum whose mysteries we are only beginning to understand. Good night.